Today I want to provide a quantitative method to evaluate the stability, crosswind susceptibility of 3 versus 4 fletch, as well as how adding a broadhead can affect their stability. Okay, there are a lot of empirical information online about how 3 fletch compares to a 4 fletch without much mathematical evidence. So today I hope to provide that. And by the end of this video, what you should be able to do is if you want to do a new arrow setup, you can simply calculate how stable your new arrow setup is going to be compared to your old one. So you don't have to spend the time and money and buy new fleshing materials, flesh them, and test them out in the field. All right, so let's get started. Let's try to guide this thought with a scenario. So I have a 3 fletch arrow here. All right, vein 1, vein 2, vein 3. This represents perfect arrow flight, is flying straight into the page. Now, let's look at this picture. What if your arrow flies tail left? What is going to push your arrow back to center? Well, in this case, only vein 1 and vein 3 is going to contribute. Vein 2 is doing nothing because it's coplanar with the axis of instability, right? The axis of instability goes left to right. Look at this case. Let's say your arrow flies high and right in line with vein number 1. Well, in this case, vein number 1 is doing nothing and vein 2 and 3 are contributing to your arrow stability. Okay, so let's go back to case 1 over here. Let's say your arrow flies tail left and each vein has a surface area of A. Well, how much surface area is actually effective towards correcting your arrow flight is only the vertical component of vein 1 and the vertical component of vein 3. Okay, so the effective surface area S is 2A times sine of 60, which is 1.732A. So even though your total surface area is 3A, only 1.732 is available to you in this scenario to correct your arrow flight. So what we can deduce is the effective surface area of veins is direction dependent. It depends on the direction of your axis of instability. So let's try to generalize this. Here in my 3 fletch setup, my axis of instability is going towards high right. All right, let's define this arbitrary angle phi between the axis of instability and vein 1. Well, what's the angle of all 3 veins? Vein 1 has an angle phi, vein 2 has an angle phi plus 2/3 pi, and vein 3 has an angle phi plus 4/3 pi. Okay? So in this case, how much surface area is contributing to correcting your arrow flight? You have this vertical component vein 1, right? The surface that's orthogonal to your axis of instability. You have this orthogonal component of vein 2 and orthogonal component of vein 3. So what is the total effective surface area? It's just going to be A times the orthogonal component vein 1, vein 2, and vein 3. All right, and these are signs of the phi angle. Now we need to slap an absolute value on them because some of these sine functions will return negative, and we only want positive surface area. Okay, so this is the effective surface area and any arbitrary angle phi. So let's graph this and see what it looks like. Here's what it looks like. As your angle phi increases from 0 to 2 pi, your effective surface area goes up and down and up and down. What is the minimum? The minimum effective surface area is 1.732A. Looks familiar, right? Where does it occur? 0 degrees, 60 degrees, 120, etc. Why is that? 0 degrees would be if your arrow goes tail high, okay? So as we shown before, only the orthogonal component of vein 2 and vein 3 are contributing. Vein 1 is doing nothing. What is the maximum effective surface area? When phi is 30 degrees, okay? So what does 30 degrees look like? This is actually drawn right here is 30 degrees. You have vein 1 contributing, vein 2 contributing, and the entirety of vein 3, okay? So this is the maximum effective surface area you're gonna get in a 3 fletch setup. we also want to know the average. We need to do an integrated average, not just averaging 2 and 1.732, okay? Because your arrow could destabilize in any arbitrary direction, okay? So if we do this integral and divide by 2 pi, we get 1.91a. How do we interpret this result? Even though the total surface area you have glued on your arrow is 3a, on average, only 1.91a is available to you to stabilize the arrow. Okay? So similarly, let's look at a standard 4-fletch configuration. I'm not going to break this down. You can just look at it at your own time. Here's what the graph looks like. Again, you have minimum and maximum. Where does the minimum occur? 2a. Where does it occur? 0 degrees, 90 degrees, 180, etc. Does that make sense? Let's say your arrow goes high right along vein 4. Well, vein 2 and vein 4 are doing nothing. The entirety of vein 1 and 3 are stabilizing your arrow. Okay, so the total surface, total effective surface is only 2a. What is the maximum effective surface area? 2.828. If you're sensitive, you will realize this is 2 times square root of 2, right? Where does that occur? 45 degrees. Does that make sense? 45 degrees would be if your arrow goes tail high, okay? And if your arrow goes tail high, you have some component of vein 1, some component of vein 4, vein 2, and vein 3, okay? All 4 veins are contributing. And your effective surface area is 2.828. Let's also do an integrated average. Your integrated average is 2.546. Okay, so you have a total surface area of 4a. However, on average, the surface area available to you to correct arrow flight is 2.546. Let's look at another niche setup, 75-105. All right, I've heard about this. I've never seen anyone do it. But, follow the same process. You have a minimum, maximum effective surface area. Look how different these numbers are. That's because your arrow is not symmetrical, right? However, your average effective surface area is still 2.546, just like a regular 4-fletch. So let's look at these results in a tabular format. You got 3 different fletching configurations: minimum effective surface, maximum effective surface, and average. This is the important information we should pay attention to. If you divide your effective surface area by total surface area of all your veins, so you're dividing 1.91 by 3, you're dividing 2.546 by 4, you get the same number. Okay, so what does that mean? That means regardless of your fletching configuration, as long as you have the same amount of total surface area among all your veins, you're going to get the same amount of effective surface area. So in a 4-fletch versus 3-fletch, because you have more veins, you can use smaller veins. How much smaller? 25% smaller. Okay, so let's say in a 4-fletch setup, your vein is 0.75 in area. Well, 0.75 times 4 is 3. 1 times 3 is 3. Okay, so you can use a vein that's 25% smaller. Well, what a surprise. We intuitively knew this, right? Only the total amount of surface area of all your veins affects your stability, and we just proven it in a rigorous way. Right, so now we know for a fact, if you go from 3-fletch to 4-fletch, your veins can be 25% smaller. This will be important later on when we talk about crosswind stability, okay? Now, how does adding a broadhead change your effective surface area? Look at this illustration here. Let's say my arrow is flying up, okay? My veins are going to produce wanted steering to push the tail to the right to guide this arrow back to center. My broadhead, on the other hand, is going to produce unwanted steering and push this arrow even more sideways. So the surface area of your broadhead is taking away the effective surface area of your veins. How much is it taking away? This delta term is the effective surface area of the broadhead corrected by the leverage, right? So the effective overall surface area stabilizing your arrow is 0.636, right? We've seen this ratio before. The area of all your vanes minus the area of your broadhead blades, all of the blades, corrected by the leverage. How do we use this equation? Let's say you have a current arrow setup. You have a certain amount of total surface area and you match it with a broadhead. Now you want a bigger broadhead. Of course, you're going to need bigger vanes to stabilize it. How much bigger? Just compute the effective surface area of your old setup and your proposed new setup and see if your effective surface area increase or decrease, right? That will tell you if your vanes are big enough for that bigger broadhead. So this allows you to just calculate your stability without fletching your arrows and doing a bunch of field tests. Okay, so that is the stabilization covered. Let's not talk about crosswind susceptibility of these three configurations. Once again, we'll start with three fletch. Okay, let's say this dash line is my vertical axis and my arrow is currently sitting like this with an angle alpha between your first vane and the vertical axis. And you have a crosswind blowing left to right. Well, how much surface area is this crosswind actually blowing on? You'll notice that vane 3 is tucked behind vane 2, okay? So vane 3 is not getting blown on by the crosswind. The area that gets affected by crosswind is just this portion represented by the blue arrow here. The vertical component in vane 1 and a vertical component in vane 2. And once again, this cross-section area is still angle dependent. So how do we express this algebraically? All we need to do is calculate the y component of these three vanes, y1, y2, and y3, okay? You're gonna take the maximum of those three y values, subtracted by the minimum of those three y values, times the area of one vane. That would give you the total cross-section area exposed to crosswind. So in a three fletch setup, we have three y values. This is a 90-degree classic 4-fletch and a 75-105 4-fletch, okay? And the total surface area exposed to crosswind as a function of alpha is just given as the area of one vane times the maximum of these values subtracted by the minimum of these values, okay? So let's graph it for a 3-fletch 120 setup. Here's what it looks like. You have a minimum cross-section area, a maximum, and an average. Okay, this is the average area exposed to crosswind for a 3-fletch setup, 1.653A. What about 4-fletch? The average is 1.8A. That looks bigger, but don't forget, because there are more fletches, we just talked about this, you need smaller vanes, right? How much smaller? 25% smaller to get the same amount of stability as a 3-fletch setup. So we can correct this cross-section area times 0.75. What do we get? 1.35. See, for a 3-fletch is 1.65. For a 4-fletch is 1.35. That is about 20%. So for the same amount of stability, a 4-fletch setup is going to be 20% less susceptible to crosswind. All this buildup leads to here. This is why I shoot 4-fletch, okay? If you're getting sufficient stability, a 4-fletch will perform much better in a crosswind. Now, this is why I included 75-105. People call this advanced crosswind stability setup. I really don't understand why. Look at this. The average area getting blown on by crosswind, 1.78, is only marginally smaller, right? So it's only marginally better in crosswind, but it has a huge problem. This is why I computed the S ratio. S ratio is the quotient between the maximum cross area and the minimum cross area. In a 75-105 setup, this ratio is the highest among these three. So why is that not good? When the wind is blowing from the side, depending on which direction your arrow is exposed to crosswind, the tail of your arrow is going to move like this, right? when the maximum area is exposed to the crosswind, it's going to kick to the right, come back, kick to the right, come back. That just can't be stable. So I really don't understand the 75-105. So now we understand the stability and crosswind susceptibility of these three broadheads. Three fletching configurations. Let's talk about clocking your broadheads. So here I have two dashed lines. This line represents the direction of maximum stability against pitch and yaw. So if the tail of your arrow kicks out this way or this way, your arrow is going to be most stable. Okay? It is also the direction of minimum wind drift. If wind comes in this direction, your arrow will be affected the least. So if you have a two-blade broadhead, this is how I would put it. The long edge is going to go along one of the vanes, right? Because in this direction, your broadhead is going to produce the most amount of unwanted steering. So you want to align that with the strongest steering offered by your arrow, okay? You want to align that with the direction of maximum stability. In this configuration, the broadhead is also most susceptible to crosswind. So you want to align that with the direction of minimum wind drift of the vanes, right? You don't want maximum wind drift on the broadhead and maximum wind drift on the vanes. So this is how I would clock a two-blade broadhead on a three-fletch configuration. By the similar logic, this is how I would clock a two-blade on a four-fletch, okay? You want the maximum surface area of the broadhead going with the maximum stability and minimum wind drift. This one is tricky. We have minimum stability and minimum wind drift together. Maximum stability paired with maximum wind drift. So if you put your broadhead this way, well, you're now aligning with maximum stability with maximum destabilization with the broadhead. So this seems to be a good thing, but your wind drift is going to affect your vanes and your broadhead the most in this direction. And you run into the same dilemma if you run your broadhead vertically, right? You're going to have maximum wind drift on the broadhead aligned with minimum wind drift on your vanes. This is good, but you also get minimum stability. So in this case, I guess just put your broadhead however you want. It doesn't really matter. Okay, let's give you a practical example. Let's say I've been shooting a three-fletch AAE max stealth, and I want to switch to a four-fletch setup. I'm going to go with a smaller vane, the AAE max 23, okay? The max stealth is 2.6 inches long. The max 23 is 2.3 inches long. I want to find out if my proposed four-fletch setup is going to be as stable as my old one. So let's just go about doing that. First of all, just download the picture of your first vane and your second vane, okay? And we're going to calculate the surface area of these vanes based on these pictures. So how do we actually go about doing that? You need to download a software called ImageJ, okay? ImageJ right here. It's free. It should take you 2 minutes to download. It's only an exe file. So now let's go about calculating the surface area. What you're going to do is click File, Open, and just grab the picture of, this is the max stealth. All right, so now you open this in ImageJ. Well, right now the software doesn't know how big the vane is, so we need to tell it how big it is, okay? So we need to set the scale first. First thing we're going to do, grab your line tool and just draw a line at the base of the vane here, okay? We know this vane is 2.6 inches long, and now we need to tell the software that. So you're going to click Analyze, Set Scale, 2.6 inches, okay? I'm going to apply the scale. Now, ImageJ knows how big it is. We're going to match the surface area now. Grab your polygon tool and simply trace around the outline, You can zoom in on this. You can't move it while you're grabbing the perimeter, so it's just zoom in and back out to move it to a different area. Now, make sure you don't accidentally grab the base of this vein, okay? This part gets glued onto your shaft. It doesn't actually stick out beyond the shaft. So now we can just right click and complete the selection. I can go edit this and move this down a little bit. Move this a little to the left. All right, so now we've selected the area of this vein. Before we measure the area, let's go to Analyze and Set Measurement. You want to turn on area and centroid. Okay, so we'll click OK, click Analyze again, and measure. This is the area, 0.699 inches squared, which is called 0.7. Okay, so your total surface area is 0.7 times 3, which is 2.1. Okay, we'll just go through that. 0.7 times 3, 2.1. All right, remember that. So if you do a 3 fletch AAE max nails, your total surface area is 2.1 inches. Let's see if the 4 fletch max 23 can beat it. Okay, so this is the AAE max 23. Let's do the same thing. Draw a line at the base of the vein. Analyze, set scale. We know this vein is 2.3 inches long. Set scale, and then we can measure the area. Grab your polygon tool and trace around the outline. I'm gonna right click to complete the selection. Move this down a little. The shoe ain't that big. Okay, so go to Analyze and Measure. Oh, here's my measure window. Okay, so these veins are 0.645. Let's see what 0.645 times 4 is. There you go, 2.58. We only had 2.1 inches for the max dells, and now we're up to 2.58. So you know that your max 23 in a 4 fletch configuration will be more stable than your max dells in a 3 fletch.